You know, in materials science, making a new alloy can feel a lot like baking. You've got your recipe, right? A phase diagram that tells you exactly what to mix and at what temperature. But have you ever followed a recipe to the letter and what came out of the oven was, well, not what you were promised? Today, we're going to figure out exactly why that happens. So, this is the big question, isn't it? Why is there this gap between the perfect material our scientific recipes promise us and what we can actually make in a real lab or a factory? Well, the answer lies in two super powerful but totally different ideas. To really get this, let's use an analogy. Think about a road trip. You've got a map that shows you where you're going, your final destination. But then you have the actual territory, the road itself, with all its traffic, its detours, its speed limits. And this right here just nails the difference between the two concepts we're talking about. Thermodynamics, that's your map. It shows you the final, most stable destination a material wants to get to. It tells us what's theoretically possible if you had, like, infinite time. But kinetics? Oh, that's the journey itself. It's the messy reality of the path you take, the roadblocks you hit, and how fast you can actually go. It tells us what's practical in the real world. Okay, so let's dig into the map first. Thermodynamics. This is all about the ideal end state, that perfect final destination for our material. You see, thermodynamics basically operates in a perfect world. It's designed to calculate the point of lowest possible energy, a state of perfect balance we call equilibrium. It's kind of like saying that if you had a jumbled pile of bricks and waited for infinity, they would eventually settle into a perfectly stable pyramid. Thermodynamics tells us exactly what that pyramid is supposed to look like, but it completely ignores how long it would take to get there. And listen, this isn't just some abstract theory. It's incredibly useful. Thermodynamic models help engineers predict what mix of materials is going to be stable, they set super important safety limits, and they let us sift through thousands of potential recipes to find the really promising ones. And a huge tool for this is a framework known as CalPAD. Yeah, CalFed. It stands for Calculation of Phase Diagrams, and honestly, it's been an absolute game changer. It's this powerful computational method that has become essential for building the very maps that materials scientists rely on to design new alloys with just incredible precision. Okay, but a map is only one part of the equation, right? Now let's talk about the other side of the coin, kinetics. This is where we leave that perfect theoretical world and get our hands dirty on the factory floor, the world of time, speed, and what's actually practical. So kinetics is all about one question: how fast? It asks all the tough questions that thermodynamics just ignores. Sure, those bricks want to become a pyramid, but how fast can they actually move? Is there enough energy to even get them started? Kinetics is the thing that deals with all these real-world barriers and speeds. And these are the factors that really control the journey. Things like cooling rate. I mean, if you cool steel slowly, you get one result, but if you quench it in water really fast, you get something completely different. Or diffusion. That's basically the speed limit for how fast atoms can move around. Kinetics has to model all of these hills and roadblocks that determine what you actually end up with. And yeah, just like thermodynamics has its toolbox, so does kinetics. Engineers use some seriously sophisticated software, like this one called DICTRA, to run these complex simulations. They can actually predict how a material's internal structure is going to change minute by minute during the manufacturing process. It's pretty amazing. So you've got the map, thermodynamics, and the journey, kinetics. You might be thinking, all right, so are these two things at odds with each other? Well, no way, not at all. In fact, their real power comes from how they work together. And hey, don't just take my word for it. The research on this is crystal clear. Across the board, scientists see these two approaches as partners. They're not competing. They're just giving us two different but equally vital pieces of the same puzzle. So it all comes down to knowing which tool to pull out of the toolbox and when. If you need to know if a part in a jet engine is going to be stable for 20 years, you're going to start with thermodynamics. But if you need to optimize a 10-minute heat treatment on an assembly line, that's a job for kinetics. It's like using the map for the big picture, but a GPS for the turn-by-turn directions. Okay, but this is where it gets really cool. That gap between what's possible, according to thermodynamics, and what's practical, according to kinetics, well, it's not a problem. It's an opportunity. It's a space where engineers can create materials that, if you just looked at the map, shouldn't even exist. I'm serious. Some of our strongest, most cutting-edge materials get their amazing properties because they are not in their most stable equilibrium state. They are, basically, materials that we've deliberately taken on a weird detour and then gotten them stuck there on purpose. This is the absolute magic of what we call metastable materials. Think about a high-strength steel sword. A bladesmith heats it up, then quenches it super fast. That process traps the atoms in this high-energy, really stressed-out arrangement that happens to be incredibly strong. And because the kinetics, how fast the atoms can move, are just unbelievably slow at room temperature, that strong structure is effectively frozen solid. It can't relax into its softer, thermodynamically preferred state. So it's pretty clear, right? To really master materials, you have to master both the map and the journey. For decades, doing both at the same time has been incredibly difficult. But now, there's a powerful new tool that's changing the entire game: artificial intelligence. What AI is doing is giving us, for the first time ever, the ability to create a kind of super map. One that doesn't just show the final destination, but also models all the possible routes, the traffic jams, and all the shortcuts of the journey all at once. So how does it actually work? Well, it's pretty incredible. Researchers can feed an AI model all the thermodynamic data, the map stuff, and all the kinetic data, the journey stuff, about speeds and energy barriers. The AI then crunches all of this and learns the incredibly complex relationships between them. It starts to understand not just the destination, but how every little change in the journey affects the final outcome. The real breakthrough here is that AI smashes through a huge roadblock: the unbelievable amount of computer power needed to run those traditional kinetic simulations. It used to be way too slow and expensive to do on a large scale. But AI can chew through these massive data sets and spot patterns, making it possible to design and test new materials virtually at a speed and scale we couldn't even dream of before. So at the end of the day, that phase diagram, that map, is really just your starting point. It's an absolutely essential guide for sure. But the true art and science of creating the next generation of materials, that all lies in understanding and controlling the journey. It's about manipulating time, temperature, and speed to engineer the impossible. And that really leaves us with a mind-bending question, doesn't it? With AI now helping us build this complete picture, a perfect map of both the destination and the entire journey, what new frontiers are we about to unlock? What incredible new materials and possibilities are just waiting out there for us to discover? Thanks for joining me.